Record on the cloud. All right, so share screen. Can we paste here? Okay, everybody can see my screen, right? The whiteboard.
Yes.
Okay, great. So this is the first question. Supposed to be an easy category question, but it took me a while to really match my answer with the expected one. So the question is as follows, right? It's a two-player game, and Alice and Bob, and Alice starts first. So you're given a number n, and then on each turn, you have to make a move based on these conditions, that you choose a number x between 0 and n, and they are not included, like 0 and n are not included. And you have to pick the number x such that it divides n. So the remainder when n is divided by x would be 0. Once you play a move with a certain number x, then you pass on to the next player the difference between n and the number that you played with, right? And then the other player can make the move. And the game continues until a player reaches a situation where he or she cannot make a move. And by that, what we mean is either you cannot find a number in this range, or even if you can find a list of numbers, none of them divides n completely, right? So one of these conditions, you will get stuck at one of these conditions, and that's when the game ends. And in that case, the player who runs into this situation will lose the game, right? So these are the rules. Now the expected output of the question is that return true if and only if Alice wins the game. And this constraint is important, that you're running under the assumption that both players play optimally. At the high level makes sense. We can take some examples, but so let's go over some examples here. So I'll go with the ones that we have in the problem description first. So let's say n is 3 and Alice is playing first, right? So what are the options available to Alice for playing when she has to make the move?
1 and 2.
1 and 2, right? Because it has to be greater than 0 and less than 3.
Yeah.
And out of
But I think 2 won't be possible, no? Because
right,
it's not
exactly.
divided. Okay.
So 2
Okay.
cannot divide 3. So the only possible option is 1, right? And when that move is made, the remainder is the number that Alice passes to Bob is 2, right? And then for Bob, similarly, the options are just 1, right? And possible will again be 1. And then Bob passes 1 to Alice, right? And for Alice, at this point, there are no options, right? Because you have to pick a number between 0 and 1, excluding the boundaries. So at this point, Alice loses. And the answer would be false, right?
Okay.
So this is how the problem goes. Anybody wants to have tried this or how to go about it?
No.
You want to just, what is like, how would you can just think aloud and we can go over the
Okay,
ideas.
so what I found in this problem was, first thing I observed was like whenever like Alice, like it's a losing state is like when you reach the number becomes 1. That is the
Correct.
losing state.
Right.
Right. So then I tried. I took some examples like 2, 3. So
Right.
I saw this pattern. Like every time you choose a even number, so
Right.
Alice gets to make these moves optimally. So in an even number, the number of steps would be such, like when the game ends, is
Right.
like Alice would win. Alice would win. But
Okay.
let's say if Alice somehow gets into a state where she has an odd number to play with, right?
Okay.
Then because then she can't get out of that state,
Mm-hmm.
because the only thing in where she wins is when she has an even number to play with. Like, let's say
Right.
even if, let's say we started Alice starts with a odd number, but somehow it becomes even. Let's say Bob doesn't play optimally, then she
Right.
can win. But here the question
Yeah.
states that they both play optimally.
Correct. Correct. So yeah, I mean that's good that you picked up that pattern. It took me a little while to get there, but yeah. So this is essentially. I'm sorry. Who was the one? Who was the one talking?
It was Raunak.
Oh, okay. So yeah, so Ronak had the, right idea about identifying the pattern, right? About this even and odd stuff. Um, that the eventually the solution you'll get is if you are given an odd number, you will lose, and if you give an even number, you'll win. But one thing is you catch that pattern, but the way I approach that, maybe I can quickly, share that, because this thing is tricky, right? Assuming both
Yeah, yeah.
players play optimally. Once you start walking through certain examples, you run into questions about how are you going to determine that optimal path, right? It's more like looking ahead in the game. So let's go over, thanks Ronak for the idea there. You have the right thing, but I just want to quickly go over some examples. So let's say we take N5, right? Um, so the options are 1, 2, 3, 4. And here the possible moves based on the second condition are only 1, right? That's the only possibility that divides 5. So the number I'll pass to Bob is 4, right? And now for B, for Bob, it will be options are 1, 2, and 3. Now here, possible moves are 2, right? 1 or 2. Right, and that's where it gets interesting. It will eventually wrap around the same idea that Ronak proposed, but just to get there, right? So possible moves are 1 and 2. So what are my options? If I play with 1, then I'm passing 3 to Alice. And if I play 2, then I'm passing, if I, then I'm
You
passing
can't
2.
do you can't do two, I guess, because it does not divide.
No, it divides 4, right?
Oh yeah, yeah. Sorry, my bad.
Yeah, yeah. So, right. So these are the two possible moves I can make. Now, let's say I go with first one and I pass 3, right? So in that case, my Alice has options 1 and 2, and possible moves would be oh, just 1, right? And then I will pass 2 to Bob, and Bob can do just one option available, and then and at this point, Alex gets just cannot make a move, right? Because you get 1 and you return, you lose. So this is the case when Bob chose 1 here. But if you'll see that if Bob had chosen 2, then Alice would have 1 possibly. So let's go with quickly this option. So if you get 2, then I'm going to pass 2 here, and in that case, Alice would have only option to play 1, and then I'm going to pass 1 to Bob, and in that case, Bob loses, right? Everybody understands the flow, the way I was navigating this. So uh, let me know if there are any questions any point. But the point I was trying to make is I tried, when I was solving this question, I tried with N5, and it took me a while to really understand the pattern here, like which move should I make, this or this, and what should be the criteria to define that, right? Um, and it turns out that any player who gets, and the formula is that any player who gets an even number, there is a possibility that he or she can play a move which will make that player win. So in this case, I'm saying that, for example, Bob got 4, right? So this is saying that there is a move that Bob can make that will make Bob win. And similarly, if Alice would have gotten, let's say, n equals 6, you would be able to enumerate a solution where Alice would win. So does everybody see this, understand the way I computed this?
Yes, understand.
Okay. So, I mean, this is the gist of the thing, that identifying this pattern, but and I arrived at this working through certain examples. So from that perspective, it wasn't an easy question for me because I really was getting lost here and I was getting into dynamic programming and whatnot.
I I think the
So
tricky is they ask for return true if and only if Alice win the game.
right, that is another thing, right? I was also thinking about that, but but I couldn't get, much out of it. If you have, would you like to elaborate on that? How that can help us here? Because I think that is possibly the trick which will,
I think like this. So
yeah,
every time like Bob or Alice can have like multiple option.
right,
But if the number is the old number,
right,
so every time Bob only choose one. That means Bob can, for example, n equal 5, n equal 4, Bob can
right,
choose 1 or 2.
sure,
That means the Alice will win the game if Bob will be choose 1 or Bob will be choose number 2 and Alice will be win and Bob will
uh-huh,
be low. But on the tricky is written true if and only if Alice win the game. That means any case the with the number one, every number can divide for number one, right? So that means every time the Bob only choose number one and Alice will be lose the game, right? Because they say Alice will be win the game if and only if, but if the Bob only choose number one, so
uh-huh,
the Alice will be for sure will be have a 1K lose the game.
right,
Yeah, it's difficult to plan because
yeah,
in the multiple option for the choosing the number you can divisible for, but if the
correct,
Bob only choose the number one, so for sure Alice will be lose the game.
right. So you are saying that because of this condition, like we have to make this thing true, right? Alice wins the game. So for that flow, then Bob shouldn't be choosing 1 based on a problem description, because in that case, Alice will lose. Is that
Yes, that's what I
right?
mean. Yeah.
Yeah, yeah. So yeah, I mean, I agree with that point, that I was thinking around this, but I couldn't really capture the whole idea. But thank you for coming up with that. But I mean, even given that point, right, as of now, I think it comes down to a simple if clause, that if n is even, right, then you'll just return true, that you can win, otherwise false. Uh, I'm just literally writing very shorthand, but this is the whole gist of the problem, that you pass a number n. If it happens to be even, then you're saying there is a possibility, there is a way that, you know, you'll play in such a way that, Alice will win, otherwise not. But just to parse these two lines and really come up with the pattern wasn't direct for me. So from that perspective, the question was quite tricky.
One more thing
Yeah.
I want to explain here.
Yeah.
For example, you say if the number, for example, because I'm also think like this. So for example, the number coming with the even number, and
Right.
Alice start with the even. Alice start with the even number, right? So
Right.
if the Alice one Bob will be loose, Alice will be make for when Bob receive a number, the Bob will be um, receive the old number, right?
Odd number, right?
Yeah.
Yes. That's
So,
right.
but if we use the even number and we minus for like because an,
Should we
because
take an example of an even number?
because I'm thinking like if we have the even number, we cannot divisible with the any old number, right? We can. Yeah,
We
we can,
can, we
right? Yeah,
can,
we
we
can.
can. So here possible moves would be like 1, 2, and 3. So depending on, I mean, I would have to enumerate solutions here, but the possibilities are that I can pass 3. Uh, I can pass, I mean, in the same order, like 5 or 4 or 3 to Bob, right? And so the point is, if we iterate through this solution, there would be a way where, based on how each player plays the move, Alice, like how Alice plays the move, then we can ensure that Alice wins the game. So I don't know if you want to, if we want to go over this steps, or is everybody good with the idea? Anyone wants to go over this workflow? All right. I am taking that as a no. But if anyone wants to, please raise your hand. Okay, so in that case, so there are essentially two conditions, right? If n equals 1, then of course you're in return false. But if n is even, then you're going to return true.
I have a question.
Sure.
How would you solve it programmatically? I mean, just
Right.
throw an if and else, not like just look at the pattern and say, okay, if it's
Right.
even, then you return true.
Correct, correct. So that's a good question, and that's how I tried. So maybe I can share my idea how I was trying to solve. I haven't really fully, completed it, but my idea was, let's see, uh, maybe I can start write some, high-level pseudocode. So my idea was I'll have a function like, oops, let's say bool divisor game, and I'm given a number n, right? So here, if n equals 1, should return false. Otherwise, here's the, like I said, I haven't finished the logic, but this is what my thought pattern was. That I want, so if I can make a move, then I'm saying, let's say my result is true. I can make a move in my current state, but this is the default value I'm taking. Now, how I'm going to reverse is, let's say I start from I equals n minus 1 and I is greater than 0, I minus minus, right? And I would say, so if if I divides n completely, then my goal here is I should return the whatever my result is, and I should make sure that my opponent doesn't win, right? I can, so if I say opponent can win. Oops, I should started writing it wrong. Thing. And I pass n minus I. So this is how I was approaching it. I have to write the logic for this function. Essentially, in this function, I have to go over something like similar, but I mean, exploring my options from the opponent's point of view. If does that make sense? Like, it's more like a feedback also because I haven't completed this logic here, but this is how I was thinking.
So is that for Alice move or Bob move? How do we know?
Yeah, right. So this is, I was thinking from Alice move perspective, but you're right that maybe I should make this generic because then this will be like back and forth, right? So maybe I should make it like,
So can you not use the divisor game itself, a function, and make it recursive there instead of the opponent can win?
yeah, actually that's true because that's exactly the logic I'm going to follow, right? So I should say, now do I need this? Probably not, right?
Yeah,
I mean,
because if the result, yeah.
yeah, I mean, you're right because I'm going to follow the similar logic when I call with the smaller, this difference.
Actually, I tried this approach. The main
Okay.
problem with this approach is like the problem suggests that everybody plays optimally. So
Right.
if you try to explore all paths, so what happens is if I get an odd,
Yeah.
let's say I get an even number, okay, and somehow I select a factor of that number, which passes an even number to the opponent.
Right.
So the opponent will win, okay, because he has got an even number. So there will be like, how do you decide out of all these paths what is the optimal path that the game is going to take? So for that, once you start, like, I wrote the code for this only to find what are all the paths and where Alice is winning and where Bob is winning. And once you see that for, let's say, 3-4 examples, and then you see the optimal is you take an odd number always out, like, and that is 1. And I'll tell you why. So what happens is, let's say
Do you want to
have
share your screen, or this is good? Like we can either way.
actually I'm phone, so I don't I can't.
Okay. No problem.
So what happens is, so let's say I have an even number, okay?
Okay.
So if I subtract, so its factor is going to be something, right? So when I subtract it from it, so I'll pass an even number. I have an option to pass an even number to the opponent, or pass an odd number to the opponent. But if I pass an even number to the opponent, so he can anyhow pass me an odd number, right? So that's the main problem. I took that example with, let's say, 4, right? Now I have 2 options. Either I can pass 3 to the opponent, or I can pass 2 back to the opponent.
Right.
So what happens in that case is, I don't know how to explain
No,
this.
I think.
How do I explain the?
Correct me if I'm. Oh, sorry. Go ahead.
You mean like both player play optimally? That means every time they take only number 1, right?
Yeah. So the main idea of the game is I want to pass the opponent an odd number, so I get back an even number, so that I win. But
you're not guaranteed that when you pass an odd number, your goal is in your mind, you're playing the game with this strategy that when you pass an odd number, eventually you get back an even number, right? But the opponent can play it differently and you can land in.
So the main problem is, like, if you subtract an odd number from an odd number, you'll always get an even number. That's the property of odd numbers, right? So if I pass an odd number to an opponent, I am definitely going to get an odd number back. Oh, sorry, an even number back. But I can't make the opponent give me back an even number once I get an odd number.
Oh, okay.
Can does this make sense? Like if I have if I have an odd number, I can't
Right.
force the opponent to give me back an even number. But
Mhm.
if I have an even number, because of the properties of even number, I can get back an odd and even both.
Okay.
So
Right. Yeah.
there is no way to force a
Right.
move.
Right. And that's where, like, either you think about that exhaustive search, which is not possible, right, given a very
Yeah.
large number, um,
Yeah.
or not even exhaustive search, right? It's more like controlling the other player, which you
Yeah. So
cannot.
so only options I get in the game is when I have an even number, I have the ability to make the opponent give me back a even number or a odd number, if that
Right.
makes
And
sense.
that's the challenge. And that's the
Yeah,
challenge of the game,
that's
right? Yeah.
yeah. So the optimal move comes out to be every time I subtract one, right? Because in case of when I have an odd number, I don't have an optimal move, right? So
Mm-hmm.
I give the opponent the opportunity to make a mistake. If he somehow gives me an even number, I will win,
Right.
right? But he also is playing optimally, so he every
Right.
time gives me back an odd number. So
Right.
that's how this game is played optimally, and that's how
Yeah.
every time we are subtracting one only, everyone is choosing one only, because only in terms of even numbers we have the option to make a mistake of giving either an even or an odd number.
Right. Yeah, I think somebody was proposing this idea of subtracting one, so coming back to that one. But yeah, it comes down to understanding the pattern of the game and where like you articulated the tricks, right? When you can,
Yeah.
if you get even, what are the possibilities? If you get what odd, what are the, how much control you can have over the opponent's move. And that's where this pattern identification, like once you have few examples, you define this pattern, and a lot of people have proposed this solution, like identified this pattern, and then they just come up with this pattern that I wrote first, that if you get an even number, then you win, otherwise not. But yeah, I mean, that's where I found this question quite tricky. Does everybody see the, the idea that, I'm not sure who was on the call, who was
Yeah, he was Ronak again.
Ronak? Okay.
Yeah. Well, actually, he says is right, but here in what you're proposing here,
Yeah.
in this for loop, when you are saying n modulo of I equals 0, it means when it is going to be even, then only you are going to pass n minus 1, right? So
No,
at that
that's
time, you
true.
are at least sure that it is going to be,
No,
you
this
are
is
going to
even.
win.
This is not about even, right? This is just modulo, but I think what Ronak was talking about is this loop. So
Mm-hmm.
even though you have a lot of options here,
Mm-hmm.
and there might be more than one option which will satisfy this condition,
Mm-hmm.
right? But the question is which option you should go for that maximize your chances of controlling opponent strategy,
Okay, but in
right?
that case, instead of returning here directly, return
Uh-huh.
result, and then you're ending with divisor game, you can
Right.
keep on going in this loop, okay, and
Yeah.
keep on seeing till your result doesn't become true, right? You can try other
You can try
options also, right?
other,
So that is
yeah.
what I was thinking. Yeah, but he may be right too because he has been
Yeah.
studying it a lot. Yeah, that's good.
No,
Yeah.
no, but I think
But
your
there is a
point
possibility
is,
of
yeah.
doing it the dynamic way, the recursive way, and then we can actually
Hmm.
convert to memoization,
Yeah,
something like that.
right. Where you're kind of exploring these different paths and keeping them,
Yeah.
store
So
them somewhere, and yeah.
yeah, because any path returns true, then you are winning it, right? So if you
Yeah,
try all the paths, at least one path will return true, right? If it's a if you are on the even side,
right.
correct? It
Yeah,
has to win. That is what I was thinking. Yeah, but yeah, it's a good thing to think over or try again.
yeah.
Yeah.
So yeah, so I don't have the full working solution based on this idea, but I think we have few, approaches, right?
Yeah.
If you want to do exhaustive, you can store results here and do it that way, or based on, you know, the pattern identification, there is another solution that will really sort of prune this thing, right? Rather than exhaustively searching, you're really nailing down the path that you want to go.
Yeah, but I think the interviewer would want to have a solution like the one you are proposing, and also,
Right.
yeah, what Ronak was saying.
Right.
Yeah, instead of just saying, okay, if it's even, then I'm going to
Yeah,
win.
yeah,
That doesn't
sure.
make
I
sense,
mean,
right? Yeah.
it doesn't make sense. It's like, how did you even arrive at that,
Exactly.
right?
Yeah.
So we have to talk about, you know, this whole methodology. And like
Absolutely.
Ronak was explaining, if even, then this is how you're controlling.
Yeah.
So, yeah.
I would say it's a good explanation from both of you. Yeah, absolutely.
No, thank you. Thanks, Ronak.
Yeah.
So good to move with the second question then.
Yeah, I would say, yeah.
Okay, cool. So let me pull the second question here. Oops. I can just quickly bring up, I have to look for the question, but I do remember it, so clear. Okay, so everybody can see my screen, or did I pause?
Yes.
Yeah, okay. So the second question is about that you're given a list of words, right? And your goal is to find 2 words in that set such that product of their lengths is maximum amongst the, you know, different words that are given. And the constraint there is that the 2 words should not have any common characters. Right? So that's the idea of, that's basically what the question is asking for. And I had an example, I think, let me stop sharing because I need to pull that screen where I have the question. Is there a way to move this? Okay.
No, I don't think you can move that once you're looking.
Yeah, that's fine. So the problem was, I think, can you still see my screen though?
Yeah, it is the whiteboard, right? Yeah, whiteboard is still visible.
Okay, whiteboard is there. Yeah, so here's an example. You're given like this set of words, and the answer is that there are these 2 words, right? No common characters, and the product is 4, and that's the maximum, like the product, best possible product you can get based on this given condition. Is the question clear to everyone?
Yes.
Yeah.
Okay. So yes, there was another example where you say like if your input is a comma something like this, then the output will be 0 because they have common characters and no solution possible. So that's the question. Anyone wants to go for it?
So the character here either lowercase or uppercase.
Yeah, there you can assume them to be all lowercase and in the English alphabet set. yeah, so does that answers your question?
Yes.
Okay. So anyone has done this or wants to think, brainstorm about this now? I mean, not literally going into optimized solution or anything, but let's, if you haven't attempted, then what would be the first thing that comes to mind? A brute force approach or?
So my brute force would be like, I would create a map that the
Okay.
key is the word and the value would be the set of character.
Okay. Set of characters. So this would be like you're saying like a hash set or like just,
like kind
okay.
of a hash set.
Okay. So essentially you're trying to capture then in each word, what characters are present.
Yeah.
Right. Okay. Then.
So let's say now I have all of them. Then I can probably have a two for loop to walk through the map and find the maximum length so far. So the constraint is for two words if they don't share the same character. If we can look up the value in the map, we would know whether they share the same character or not, right?
Right. Yeah. So you touched upon this idea about identifying common characters using hash match map or further this set. And how would you go about the optimization goal, product of lengths?
No, this is not optimized. This is like I could have two for loop.
No,
right?
no, I mean, that's true. I mean, not in terms of optimized solution, but I'm saying that once we identify this, right, common characters part in your solution, I think you have the point that when you have two for loops, you're essentially going every pair of words.
Yes.
And then you're trying to compute their, lengths, product of their lengths. And, at the end, you will have the maximum. Is that right?
Yeah.
Okay. So everybody see that solution? So maybe I can just quickly write pseudocode so that everybody is with me on that. It's like once you lose control of this text box, you can't get it back, it seems. So we are saying that we are maybe, you can go till n. So if there are n words, and then you can go over like essentially two for loops, right? So you're matching each word with the next possible word. And I'm assuming that, let's say I have a hash match here. Oh, this is fun. Okay, so, and then I can say so I can pick my words here. So word one is words of I, and word two is words of J, right? And I can say if they have no common characters. And this is where I think you were suggesting that we can use this hash map. And okay, I should move here. So if they don't have common characters, then I'm going to, let's start here. So then I'm going to have the product of their lengths. And at this point, I can say if my product is more than the max I have so far, and I can initialize max, then I would update the max, right? everybody kind of agrees with this like basic solution?
Yes, I agree.
The other solution I have is to, kind of have an array of 26, and then, let's walk through each.
Right. So I think before, can I just, add one point, because I think you are leading to the next thing that kind of naturally flows through the solution.
Yeah,
so
sure.
we wrote this high level code, but we didn't talk about this function, right? Have no common characters. So there are different ways. One way that someone proposed here, I'm not sure if I got the name again, but we were using hash map, right? Where the idea was that, for example, for the first word, A, you're going to store a hash, let's say you're going to say word 1, and you can say A is present. Then you can say word 2, and I have A and B, right? So you will construct something like this, and then this is what you're going to use in this function. And the complexity of this would be dependent on a couple of things, but the idea is like a quick lookup. So you can look through your hash map and you can get these entries and you can search through them if this is present or not. But I think that's leading to the idea that whosoever was talking recently, you had an idea about using some counts, right?
I think it was Leon who was talking. Yeah.
Oh, okay. I'm sorry, I'm not able to see the
I
participant.
know. Yeah.
Yeah. So yeah, so Leon, you had an idea about the counts stuff. Somebody was proposing an idea, right, about using an count array or.
I think he is not active now. Yeah. Okay.
Oh, okay. Yeah. So in.
Yeah, we
So
can
let's
also
continue.
use a bit vector, and that would be much more efficient than.
Right, because right now, if we have a word with, let's say, I don't know, 20 characters, then essentially we are saying that we are going to have this set with 20 characters and we would still have to search through it, right? So bit
True.
operators. So that's where we are thinking of reducing the complexity, right? And can you elaborate on this idea?
Yeah. So basically, for every alphabet, we will try to set its in a bit because currently our grammar has 26 characters.
Right.
So it means that the 0 bit is set if A is present, first bit is set if B is
Right.
present,
So
and so
let's
forth
say
and so on.
alphabet. So you're saying something like this. You can have a 26, character like this array, and you can say if A is present, you'll set it to 1. Otherwise,
Not really.
okay.
I will not have an array. It will be an
Okay.
integer because integer has 32 bits, right?
Uh-huh.
In general, like on a processor. So what I will do is, for example, let's consider our case X, and so X will become let's say A is present, so the X is equal to X right shift
Okay.
and something like that. X and X or sorry X or and then 1 or X or.
Oh, XOR operator, you mean?
No,
Or
bitwise
just,
operator or, yeah.
okay.
And 1 right shift.
Right shift.
I think that one should be left shift,
Sorry,
not right
left
shift.
shift. Sorry, left shift. Sorry. Left shift, and then character, whichever is the character, minus A. So
Oh, I
that
see
will
what you're
basically
saying.
shift it to that, and then just
Like
try
if the
to
character is this, then.
ch minus A. Yep, that's true. So now this will
Okay.
generate the number for every like for every alphabet. And once we have that, we can do it in O of one time, right? We can basically see if there is an intersection or not by doing an by doing an
Oh, I
and of this
see.
material.
Okay. So
But
rather than storing these, you're saving this whole, so
Yeah,
lookup
because
and space.
yeah,
yeah.
Okay.
Also,
good idea.
also because if you are storing these characters, right, then
Mm-hmm.
you have to do either you have to hash those things
Sure.
or you have to look up one by one character, right?
Yeah, I think hashing still can be avoided that, okay, if I just, keep storing, but I would have to do a search or
Yeah,
it's not a simple
that's
lookup.
true. That's true.
Yeah, and the space would be another constraint because I will be taking up that much space. So with your solution here, we are saying that as we navigate the strings, so let's say we are at this step and I'm trying to see if A is present in this one, then all I'm doing is picking that character A, which is my X, and then doing this, left shift operator and using this OR operator. So if
Yeah.
it is present, then it will return true, otherwise not. Is that right?
Yeah,
Yeah.
yeah,
Right.
But I will actually maintain the table of this X for every word.
yeah. So
So
that
for
means
example, in
Right.
case of A, it will become 1. In case of B, it will become in binary 1 and 1, which is 3, right? So all these
right.
numbers become something like that. And
Oh, you'll come up with the binary, like,
binary representation of these words.
Yeah.
And finally, I can do an and of these words to say whether there is an
I
intersection or
see.
not.
Or we may not even need to do and because the moment we find the first match, right, we don't want any common characters, right? So as long as, even if I find, A is present, I don't even need to look for others.
No. If you find the first match, but how about if the a lot of the number behind that number doesn't match with the first number?
No,
No, I think she is right. Like once you
no,
have
so
figured out there is one
yeah.
intersection, you
Right. So
don't need
because
to,
we don't want any common characters, right? So when I'm comparing A, B, C, D, like something like this, I don't need to have an or and to traverse this whole string. Once I find that compare A with A, there is a match and just return false because I can't consider
yeah,
that pair
but that is true.
because that way if the string is really long. And that
Yep.
is one optimization I can do, right? I can start by doing this search, this matching criteria, starting from the shortest string. Because that way I can prune the rest of the part of the longer string if I already find a match.
But that, like in terms of if we think this problem in terms of a bigger notation, that won't help, right? So the complexity will still be the worst case one.
Yeah, like in terms of order of this, you are saying? That
Yes.
is true, but I was thinking that within this second for loop, this function, right, would
Hmm.
add certain complexity. Is there a way that I can reduce that?
Uh, I think we must have at least the on square, and the function
Mm-hmm.
have a no common character. We can do it in the O1. Because actually we set the command of the character, but if we see the description, the character in the alphabet of the 26
Mm-hmm.
lowercase. So that means the maximum array for searching the common word only the 26, or of the 26 only O1.
Yeah. Yeah.
So
I see. Okay. Yeah, that makes it constant. Right. Okay. Sure. Yeah. So does everybody see the point? At least this idea is clear to everyone. Yeah, this was really neat. It didn't occur to me. So thank you. So the
Yeah,
point where, yeah, sorry, go ahead.
yeah, that's clear. But are we going to store these results, whatever the bit operators you are going to do, in some lookup table, or we are just going to?
So my idea is that we should be storing. Let me think. Uh,
he should store that one in the integer array, with the array have a length equal with the
Input
input
array.
length. Yeah.
Yep.
So
That
that
was
means
why should we? So even if let's say if I have something like this, right? A, B, C, D, and I have all different characters and then D, right? So once I compare this with this, in that case, I say no match. And if I just continue with next without storing anything, the moment I say, yeah,
Actually, if I can explain. So
sure,
what
sure, of
he's
course.
doing, what he's doing, he's converting every alphabet, like every word in the array to a
Uh-huh.
integer number, where each of the set bit of the number represents whether that character is set or not. So
Okay,
the
right.
length of
This
the
was
string is not affecting what the integer number is going to be, right? So this will become 15. Your ABCD will become, and
correct.
EFGD will become some integer. So
Sure.
he will iterate of all the 26. So he has stored 15 in this array. He has stored this number
Right.
in this array, and he's comparing all the pairs of these integer arrays. And the comparison of have no common characters is a constant operation, because what he's doing
Oh,
is he's
okay.
going from the 0th bit to the 26th bit of that integer, and is any of the bits set or not, like they match or not. If they match, he's returning false. So that
Yeah,
is
So
yeah.
just the bitwise
If
and should
that's a
not be enough.
constant operation. And
Yeah, that's what I was saying. You don't need to compare every bit. If you do an AND, it will give you
yeah,
whether it's whether they have intersection or not, because
Yeah, something
this
like this,
AND will
right?
give
yeah.
The
yeah.
way I
So
wrote. Is
Yeah.
that right?
yeah. So and so
A
he
bitwise
will
AND.
go from one. He will yeah.
Yeah.
So
So
I will do bitwise AND between these two.
yeah,
And if it's 0, it means there is no intersection.
right.
Otherwise, there is an intersection.
Yeah, got it. Yeah, makes sense,
Okay.
right? Yeah.
Yep.
So sure. So we would need space for these things and saving the result.
This will be an integer space, right? So it means that you need an input array size. So O of n.
Yes. O of
N. Where n is the length of the array.
right.
True.
Yes, because yeah, makes sense. So the solution we are saying is order of n square complexity, time wise, and then order of like n space, right?
Yeah.
May have to look deeper, but we got some good ideas here, right? We saw how the brute force works and then where the optimization lies. We are trying to optimize this function here. Um, make sense?
Yeah, absolutely. Yeah, that's good.
Oh, great. Yeah, so the third question, Roger, would you be able to lead that one? Or if anyone else has attempted?
Yeah, let's see. If somebody has attempted that, they will better do
Sure,
it. But
sure.
let's see who wants to.
Would have just have to drop at 9:30, so that's why, but
Yeah, feel free to drop and
yeah,
make me the host. I think looks like,
sure.
yeah, nobody has attempted, maybe.
Um, so let me make you the host.
I tried the brute force approach, but it gives me TLE.
Oh, okay. So you want to try, Gaurav?
No, go ahead.
Okay. Because at least you tried something, right? So let's
Yeah,
have fun.
okay, but I can like explain like what I tried, like the brute to start with the brute force approach.
Sure, sure.
Okay, so you're the host right now.
Okay,
Both Roger and I made you host, Roger. Gaurav, are you already? I can't see the option for
No, like you don't need to make both the host. Like Roger is host, it's
Roger.
fine.
Okay,
I will just like share my screen.
sure. Okay, thanks.
thank you.
Thanks, everyone. Bye.
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 Can you see my screen?
Yeah.
Okay. So just give me a sec. Like this is for some reason going too slow on me today. Okay, can you guys like see my screen?
Yes.
Okay. So this is the array that is like given to us, like the grid. Okay, and what we are saying that, and let me like replicate it, like just to have like one more example. Okay. So what we are saying, you can think this of a maybe bubble shooter game. Okay, where if something is connected to the top, it will be attached. It will like remain. It's a brick. Like every one is a brick. Every zero is an empty. Like it doesn't represent a brick. So if any brick is connected to the top, in this case, the first row is a top row. So any brick which is on the top will remain there in the game. Any brick which is connected to the top will remain in the game. So take the second row. Okay. Second row, first element, first one, it's a brick. It is connected to the top, correct? So it will remain in the game. This brick, it is connected to the top by its left neighbor. So this will remain in the game. This brick, it is connected to the top by its left neighbor. So it will remain in the game. Now, this brick, which is on the bottom right, it's not connected to the top by any of its neighbor, and it's not the top brick. So this cannot remain in the game, it will just fall. Okay, so there cannot be like any condition, like our game cannot be in any state where we have like this one hanging alone, which is not the top and not connected to the top. So let's remove it now, or let's keep it. Now, what will happen? And as per the questions, we are given a array hit, which determines what brick we are going to hit. So once we hit a brick, we convert it to a zero. Like we will remove that brick, and then we have to look into how many bricks are going to fall at that moment. So let's say, what if I hit the brick which is highlighted? I make it zero, correct? Can you guys still hear me?
Yeah.
Okay.
Yeah.
Okay. And then once I make it zero, like how many bricks are going to fall?
One.
Cause this brick is not connected to any of the top brick. Let's say if I make this brick as this highlighted brick as zero, like I hit this brick, how many bricks are going to fall?
Two.
Two bricks,
Yeah.
which are these two, cause like they are now not connected to the top.
Correct.
Okay.
Yeah.
So, and let's say like if we have one here, and I hit this brick at 1 0, how many bricks are going to fall?
Four.
Four?
Yeah.
Because now these four bricks are not connected to the top.
Yeah.
What if my state is like something like this, where all the bricks are connected to the top, like from two locations. Like it is connected to the top from here also, and connected to the top from here also. And I make this 0. How many bricks are going to fall?
0.
0, yes, because these bricks are already connected to the top, so they are not going to fall. What if I make this 0?
That one 0.
3.
Yeah, 3 bricks are going to fall. So hopefully, like, the question is clear to everyone.
Yeah.
Correct?
Yes.
That's clear. Yeah.
Okay. So
I think this part is clear.
Okay. So the way, like, the brute force I was trying to think of it was using the number of islands approach, like where, like, I hope like everyone is familiar with number of islands, how to figure out how many number of islands are there, where we do a DFS and figure out all the connected neighbors. Okay. So in this example, let's take like this example, whatever is on the screen. Let's say we are hitting the brick at 1 0. Okay, now how to approach this? The way I did it, whenever I hit a brick, okay, I made that brick as 0 if it is 1. If that cell is 1, then only I have to like make it 0. If the cell is already 0, then it doesn't make sense to hit it, because even if I'm hitting it, like nothing will happen. So if it is 1, I will make it as 0. And then for all the elements in the top row, okay, I will do a number of island approach, like the BFS approach. So I will start with the top row and start converting, like let me rewrite it here so it is like more clear. So I will start with the top row, taking elements from the top row which are already 1, and then start marking them as 2. Okay, 2 or something, 2, or like you can create a I believe like it's better to have a vested array, because like a Boolean vested, so that you don't need to like unmark it. So but the idea is, okay, I will mark this as 2, I will mark this as 2. So first I mark this as 2, and then I will do the DFS to mark all the connected neighbors to 2. In this case, since this is the only element, I cannot do anything about it, anything more. Now this is 0, second element, so I will leave it. Third element, I go again, I mark it as 2 since it is 1, and then I will do a DFS to figure out all the connected neighbors, and then I make all of them as 2. Right? Once I make them all of them as 2, I make a sweep of the whole grid, starting from the row number 2 to the end, to see how many ones are remaining. Okay, so let's take like a better example, because here it's like not very clear. What if we have 1 here and we have 0 here? Okay, in this grid. Okay, and also let's take a couple of more elements on the right. 1 1 1. Okay, so this will make more sense now. And the goal is to hit the brick at 1 0, right, to start with.
Okay.
Okay, so this is my grid, and I will make this as 0. Now for the first row, I will repeat the same process, whatever I mentioned earlier. So I will start with this first one, make it 2, because it's a break, and then make all the neighbors as 2. I cannot, because there are like no neighbors which can be made 2. Second 0, I will leave it because it's not a break, not a break, not a break, and then I go here 2 and make all the neighbors as 2 by doing the DFS. So once I'm done with this pass where I've iterated through all the elements on the top row and make all the neighbors as 2, what I will do, I will make a sweep of this whole grid starting from row number 1 and then see how many ones I have found. Okay, so those are the ones which are the bricks which are now not connected to the top. So how many I found here?
4. Yeah.
4?
Yeah.
Okay. Now, let's say next hit is at this location, top right. Okay.
Mm-hmm.
And in this case, my grid is, because I have to like start with the same grid. Okay, so that's why I was suggesting like if we take a Boolean visited array, so that we are not modifying the existing one. So the goal is to modify this to 0. Okay, so I modified, and while I was done with the second, like the first pass, I marked all of those to the 0, whichever were 1, whichever were already fallen. So our grid was in this state after the first pass, where we found, okay, 4 were fallen. Now I make this 0. I repeat the same process. First one, I make it 2. Second 0, nothing I can do. Nothing I can do here. Nothing I can do here. This was already converted to 0 since since that was the state of the matrix, because we are hitting this break, and then nothing remaining. Again, do the sweep of the whole grid starting from row number 1 to the end. And how many bricks like we find this time?
2.
2. Okay, so 2 bricks will fall, and we will make those to 0 for the third pass. Okay, and let's say, yeah, so we keep continuing the same approach for the hit length of hits array, and then we will find all the bricks for each hit like that are fallen. So this was the like brute force approach that I followed. It passes like 8 test cases out of 16, and then it gives me TLE.
Just a quick question.
Yeah.
When they have given the input, is it like they are doing at once or they are taking turns? Like
turns, like you have to do
so
one hit
it's
at a
kind of
time.
an interactive kind of a program, right? Where it will just give you first it will hit 1, then it will hit 2. For example, in this case, right? What does this hit 1 1 and 1 0? So will it be like happen at the same time or will it like take turns?
No,
So
every time.
you are
Not
given
the
a
same time.
array of hits.
Mhm.
Okay, where each element in that array represents a location in the grid that you
I
are
see.
hitting. Okay, so you have to like start from 0 to the length of that hit. Okay, and that's how like you have a result in the form of integer array. So when you do the first hit, okay, how many bricks fall will go at index 0. Second hit, how many bricks fall will go into the index 1, and so on. So the result is array of length hits length.
I see. My another question is why didn't you store the total number of children for that node instead of iterating again and again? So when I say total number of children is like, for example, now this example is actually a little changed, but like
I can like change it like if you want. So you are you suggesting like maybe something like
yeah, I think that should be enough. Yeah.
okay.
Yeah. So what I'm saying is you do a BFS and sorry, you do a DFS and you start DFS doing from the top vertex. So from the top row only, right? So the
Okay.
0 0 is set, right? So currently 0 0 is 1, right? So you will do a DFS from there, and so you will compute how many childrens it has every node in the path.
No, I don't need to because I don't care for like how many children are connected
Because
to.
okay, that will help you because if you delete a node, you will know how many nodes will be affected because only its children will be affected. Am I right?
Okay, so So let's say like in this example, once I'm doing the DFS like here, and,
So
and my
this
goal
is
is to
make
hit
it
this
to,
break.
yeah, goal is to hit this thing. Okay. But if it knows how many of its children are there, then we can directly get that value, right? And you can get that from
Okay.
the DFS.
So
Right?
so let's say like how many nodes are
So
connected to the first one.
first one, right? So it will be 1, 2, 3, 4, and 5. 5.
Why
I'm
not this?
excluding the top one. I'm excluding the top
Okay.
one. Okay.
Okay. So there are
So
5. Let's say like
yeah,
okay.
yeah. And for the below one, the 1 0, there will be 4, right?
Okay.
Right. And for this guy, it will be 2, right? For this guy, it will be, oh, you are saying because now we don't know the direction. So no, we know the direction, right? So it will be 3.
It will be 3. Okay.
Yeah. And then when we go from,
Well, why it has to be 3? It can be more than that, right? The 3 as well as it can count the first on the one on that line as well as this 2.
no,
Yes,
when
like
you
that's what
start DFS,
Yeah, but that will
so you,
be okay.
that's what I'm trying to understand. Like that's why I was like writing this because like in case of the first one, which is here, we took the number of connected nodes to 5. Okay, but for every element, the number of connected nodes are 5. Okay, I'm not sure like why they are like 4 and 3 because if you take a look at that way, either you are storing the current neighbors. So in this case, the first one should be only 1.
no, I was just getting like how many nodes you have touched along the path. The island
Okay.
problem you are saying, right?
Okay.
So like it keeps on returning during the recursion, right? So it will just return how many children, how many nodes of 1 it has seen in
Okay.
its subpath.
Fair enough. So
That's
like
what I was
so
trying to do.
you're saying like 3 here. Like what will go for here then?
So yeah, that's becoming confusing for me now, because once
Yep.
you start doing this, that will become actually 2, right? That will become
Why
2.
2? Like it will only become 1 now. Like because you're not including the.
Yeah, the one
Okay.
towards your right side. Okay.
Okay.
Okay. And then, yeah, let me think, because if you delete 5, the 0 0, it will return directly 5, right? That 5 will drop, right?
No, they won't cause like they're now connected to the top here. Okay.
Oh, that's what you're trying to say. Oh, yeah. You are right.
Because if I make this 0, okay, none of those bricks are going to fall.
Yeah, you're right in that case. Yeah.
So that's why like I was like not trying to follow that approach because it even didn't like came to my mind like to make it count like that, but like for each hit, mark the whole grid as whatever is connected on the top as connected, and then figure out how many are the elements which are now still not connected to anything, and then collect them. Hey, Roger. So like, do you want to take like, do you have any other approach?
Yeah, so let me try something like.
Okay.
Yeah. Let me share my screen. Okay, so that was a good approach. Like so far we just discussed, and we can also look at this in a different way. Like, so suppose your top is definitely special, right? Because if anything is attached to top, that means that those guys will live, right? Hanging to that. So that's why like Gaurav was trying to first run a DFS on the first row, right? Right, Gaurav? That was the idea. That so
That's
will,
true.
yeah.
Yes, that was the idea because like top row will always like hang there.
Yeah. So now I will just try to draw some things and we will erase, we will play with it. Suppose I have something like, an island like this, maybe something like this. There is, let's call another bridge kind of thing here, which will, okay, can I draw it? So can I say this is like a bridge to a newer island? Can we think like that?
Yeah.
Okay.
Yeah.
And then we can also think there is another bridge to another island, right?
Yep.
So all these points, they are kind of special because if we delete a bridge, then our overall size will become smaller, right? Suppose in the beginning, everything is connected and one by one, you are choosing a point. There could be totally like independent, like, island. Let's see if this is not connected to top, this is a totally different case, right? But suppose all these three guys here, like these three, they are connected overall in the beginning, right? Because
Yep.
I'm assuming that this was like top, like, this guy had a top thing here, like this guy is connected to top. So does that make sense so far?
Yes.
Okay, so if any like, request comes for this guy, doesn't matter, like, it is not connected to top, so you don't care, like it will not like delete anyone even in, like, adjacent to that guy. So
Yep.
that is as per the rule of the problem. So now we may be having like lot of this kind of connections, right? Which can lead us to give, okay, so if I delete this much, what is the size, like all these guys are going to get impacted, right? So this is what the question is asking. Like if I hit this bridge, other than the bridge, who else got impacted? So that is how you can look at the question at. So now also look at it. If we have this kind of relation, and suppose I create another like component here, like another thing here. If this guys get disconnected first, then here also we have a disconnection already, right? Because now this is not connected to, even if it is like, added to this, like, there is another bridge which we will break later. It will not affect the overall like island. So far so good.
Yep.
Okay, so now look at backward. Like, so if we go sequentially from left to right, things get impact, like, whatever happened earlier, like affects the like, things in future. But if I start from the end itself, then like, things which happened in past may not be affected. All I have to do whenever I make, like, handle this case, like, the last thing which happened, if I just change the state to the previous case, like, when this didn't happen, what was the state, then we can like reorder things accordingly, right? So
Yes, makes sense. Makes sense.
okay, so now we will like, we will do exactly what Gaurav was trying to do, that okay, let's go through all these like hits, like wherever we are hitting, just remove those guys, because we don't know, like, whether they fall in this kind of situation or maybe this kind of situation. So they are totally out of question to begin with. So we'll consider, okay, just delete this if there was a request for this thing. So these are disconnected to begin with. That is your first step. So if you do that, then maybe and then do a, like, flood fill your like thing which are connected to the top. That is the second step. So maybe after that you will have this the thing I'm just showing this one. Maybe you have this kind of connections and other things are like, disconnected. Something is here, something is here, because we just broke the bridge between there. All right. So
I see. So technically you are saying just go from right to left,
right,
and then make this marks as zero, whatever the disconnection is, and then just in the end just compute once, right? How many are connected?
right. Now everything, yes, exactly. So now in implementation wise, all these values in this is like in the current implementation is 2 basically, because they were filled with 2. These are still ones, right? Now suppose I want to add a bridge. Now, this is done. This was my second step. Now I start from the back. I add this bridge here. So when I add this bridge, I will see, okay, what is the size of this island? I will also flood fill this. So eventually after this step, this will also be filled by 2. But then I can calculate, okay, when I did that, how much the size increased here, right? I will not care about if thing is already 2 and then it's fine, like, no need. Also check whether it is connected or not, because maybe there is something here which is not connected. Your bridge was here, it's not connected. So you don't worry about it. So this is your output. Like if this was like say 5, you just add it in your result and you keep doing that. Like, so because after this state, see, now you have this state already. If you would have gone from the beginning to the end, that would have been your last step anyway. You just broke this one in the, like as a last bridge, right? Is that clear?
Can you repeat again?
So let's, what I'm saying, like
the last part, basically the after that you said that we will connect the bridge.
Yeah. So suppose in theory, like, this was the first bridge which was broken. This was the second bridge. This was the third bridge, for example. But when we are going from back to, like, from this side, like, for second step, it's already has restored the, like, overall things which were connected to the, the island, overall island, which were connected to the top. So 2 is good to go at this point of time. 2 is exactly in the position it will be. After 2 is suppose also get added, the situation will be different. Like this will be like this kind of island, and 1 is now good to go. Does that make sense?
So, but are you saying that we need to first identify the bridge conditions or the bridge points? Is that what is you're trying to say?
So no, I'm not saying that, because they are already giving you like where you want to hit it.
Oh, okay. Those are the hits. Okay. No problem.
So you can have a hit here, but then you will check its neighbors, right? 4 directions, and you will check, is any value equal to 2 or not? If not, then we know that this guy cannot be bridge, right?
Yeah. Okay. Got it.
Yeah, for these guys, like, the neighbor, one of the neighbor will be 2. That just proves that there will be a bridge there.
Okay. Yeah.
So
that's a good approach. Like for my understanding, I just wanted to like recap like what you just said. So whatever the grid like we are giving with, we are looking at that grid as number of connected components. Okay, like how many components are there? Now, the first step that you said, given the hits array, we will go to the grid and mark them as like maybe whatever we want to mark them, like maybe as something else, like maybe instead of 1 we can mark them as 2,
yeah,
or -1, whatever we want.
Mm-hmm.
and then like we know like we have broken all those bridges.
Yep.
And we run a connected component algorithm, like maybe number of islands, whatever way we want, or we can use a union find.
Yep.
Okay, to figure out how many connected components are there after the bridge is broken. Like all the bridges are broken. So in this case, let's say like we get like 4, 4. Okay, the way like you've drawn the figure, and then we start traversing the hits array from the reverse, again joining each bridge at a time.
Yeah.
Okay, and then see how many connected components are like we left with. Okay, so if we have like less connected components, and the connected component which is connected to the top, it has like more elements, then that means like we have those were the number of elements which were fallen earlier.
Right. I will also write it here,
Okay.
just so that, like,
Okay.
people may follow. So first step we did, we look at the hit array, right? So you are given hit array. What I am saying, like, remove those guys from the calculation. So if there was like, 0 and 1, like, if there was 0, you don't have to do anything. But if there was a value there, you just make everything to like 0. So you can say that, go to the array, go to the like, grid, and just you perform like, grid -1. So handle hit array. Why we are doing that, we know, because we will start adding one by one.
And we want to mark them like anything else than 1 and 0, I believe, because if it is already a 0, we don't want to come back and then re-add it.
Okay.
Right.
I guess so,
yeah. So in second step, we will exactly do what you did, so that now for the first row, so first, or let's call it what should I call, top or roof. So top row, for that you flood fill with maybe, let's say, 2. Flood fill with 2. So that will give us this thing. Like, when you have only this thing, which is connected to the top, right?
Yeah. The main bridge. Okay. Yeah. The main island.
Yeah. And third, we will start going from like,
No, like just to add, like it might not be only one island, it might be like 2 different islands. Cause let's say like in the example that I gave earlier, one was connected from the left and one was connected from the right.
Yeah.
Maybe extreme left and extreme right. So we might have like 2 islands which are connected to the top.
That's right. Yeah, you can have that. And yeah, if there is another thing here which can have a bridge with this, then that can still give you like, okay, what was the size of this guy, right?
Yeah.
So same thing. So now, yeah, third step, what we want to do, we want to go from back to the end, because we want to maintain the state for all of them. So from end to beginning, you will again, like, you had handled, like, you had already removed that value, but now you will reset this value. Suppose the request was for like this guy. You remember in the first step we had changed this value, so you again go back to, like, the value 1, or and then you do the DFS, try to find how much the value increased by, and you keep populating that for each of them. So reset value, then DFS, and populate the result array. I can share the code. I am not logged in, but that is how I had done earlier. So I will send that after the session.
Sure. Yeah. Yeah, this is a good explanation. Yeah.
Yeah.
So you said, like, if you do it either through BFS, DFS, it doesn't matter, right? And then we should be able to get the results.
Yeah. You can do, like, whatever way you can calculate island, and that should work.
Okay.
All right.
Yeah. Yeah. Thanks. Thank you, Gaurav. Thank you, Roger.
Thanks, Roger.
Thank you.
That was a good explanation.
Yeah. Thank you.
Yeah.
And thanks all of the other guys like who explained the previous questions too.
Yeah, I will stop the recording now. Okay.
Sure. Yeah.